Sergio, okay. You had the comment regarding the. Sorry, so let's continue again. We had a few minutes where we spent just to figure out the technicalities of this new approach or this new technique. So this semester we're going to have ECE 303, electromagnetic waves, and I'm lucky because in this course we have seen each other in the previous course or in the course, in the prerequisite of this course, which is the electromagnetic field theory. And this class is a continuation of that class. And the elements that you learn in this, that we are going to learn this semester, they are very essential in understanding the way how we transfer information, how we process information, or how the information is affected by a medium where it is going to be transmitted. Okay, because we often we use light source as a tool to distinguish something or to detect something, starting actually from the waves which come to from an antenna to our cell phones, including also not only for communication, but also for vision. For example, the waves that we communicate with, sometimes you want to see the sun. There's a wave function over there, not a wave function. It's the propagation of waves that we use for imaging. We can also take a picture using a satellite. You can see the Earth, and maybe one of the most common ones is the Earth at night, when you see the lights spread around areas where people live the most. So that's an imaging using a specific wavelength and a specific frequency. Of course, wavelength is always inverse proportional to each other, lambda and the frequency. You can also conduct the imaging of not only a planet, but you can also change the wavelength or the frequency, and you can get more details than just a brightness spread. If you are going to see how the light is distributed on a planet, then you can get in a smaller scale where you might be interested into observing, let's say, a building or a person or taking a picture. Then you can, and always when you are trying to observe something, there is a field of view or the range that we are observing. So that's one important parameter. And then you can still change the wavelength more and more, and then it comes a moment where the spatial resolution or spatial resolution that for what you are going to observe, it will be comparable with the features that we want to understand. Now, whenever we talk about photography, there is a problem that it is not very clear how the wavelength it affects the quality of image acquisition. Okay? But the moment that the wavelength is comparable to the size of the objects that we want to observe, and not only the size, but also the resolution with which we want to observe, that moment is really a very interesting region or domain where you can really make use of general principles that you have learned in different courses. For example, when you talk about the wave, a good example of a wave is the waves in the sea, okay? Which, if I ask from you, for example, what is the approximate range of a wave in the sea, you could say in the order of meters, okay? You might have waves which progress, if they are far away from the shore, it could be 10 meters, 20 meters. Okay, so that's a wave. Okay? And now, when the waves approach the shore, what happens is that the wavelength changes. Okay, so they repeat the crest, they repeat themselves. So this is going to change. Okay, so this is going to change, and why? Because you observe, or the wave is detecting, but this is not very wave-related effect. So let's say that you are approaching the shore, and here the frequency of this wave is going to change. Okay, and also the wavelength is going to change. So now, what it used to be in the order of 10 to the power 1 meters, you go, so this is wavelength, it can be 10 to the power 1, let's say 10 to the power 2. Here, the wavelength is going to be something like 10 to the power 0. So in logarithmic scale, it's really when we have a huge range or domain for possible values for the wavelength, using the logarithmic scale, it's very scientific. An engineer should do this right away. Okay? So this is how the wavelength is going to change. But why is this? The reason is that here you're approaching the shore, okay? And then you have a response of these waves by changing the wavelength. The same thing happens each time the wave passes through a piece of glass, passes through a filter of specific polarization on your glasses when you have sunglasses. But then what is interesting about the waves is that once a wave passes through a piece of glass, which is a new material or a new medium, once it gets out back to vacuum or air, it recovers itself in all of its properties, okay? Including the wavelength, the frequency, the wavelength predominantly. Because based on what you have learned in the previous course that we took together, you know that the response of a wave with the medium is a strong function of the permittivity, of the relative permittivity of a medium. And you would remember very well that permittivity, it was a value of epsilon r times epsilon 0. This epsilon 0, we say this one for vacuum or for air. I think with this much we do remember. And this is the new parameter, which is an effect of the properties of a material, be it a piece of glass. Okay, so this much is fine, but I want to the discussion. I want to connect it to the previous what we were saying a couple of minutes ago, where we said that the waves of water waves, when we are in the sea, they are approaching the shore. Good. The point we want to make is that this wave, it can pick up the shore which is approaching this red line. Okay, and then here you have the umbrellas and the hotels. But let's assume for a moment that here you have a stone, okay, a little stone or a little shell, which is at the rock bottom of the sea. And then the question is that will this wave be disturbed by this little stone? Okay, that's the first question. For sure, we have been lucky enough, most of us, to experience that this wavelength is reasonably distinguishable once you see this shallower regions. But the question is this: can you see a shell that would be here or a stone here? The answer would be no, because the wavelength here is the wavelength is much higher than the dimensions b of this little stone. So the moment that the lambda is much larger than the diameter of a specific object, then we can say that we cannot use this specific wavelength to distinguish or to detect such an object. Now, this is what I want to connect the discussion of the waves with what we were saying a couple of minutes before, which was detecting objects, which is not very clear when we do photography, but it's much more clear when you decrease the field of view, when you see much smaller objects, such as in microscopy. Microscopy, in principle, is the inverse function, not function, it's almost, you can call it inverse function, but it's inverse operation of photography with respect to a lot of approximately, let's call this one 10 to the power minus 6 meters. Okay, we're talking about micrometers. We want to observe this, good. But to observe this, to figure this out, for sure, we cannot use these kinds of waves. But let's see, if we want to see this 10 to the power minus 6 meters, what is the wavelength which compares to this one? If we think about let's convert this to nanometers, because we're used to nanometers. At least we can pick up ranges of relevant ranges. If we convert this to nanometers, which is approximately, we want to observe this D with 10 to the power minus 6 meters in nanometers. That means that we multiply this one by 10 to the power minus 9, 10 to the power, sorry, 10 to the power plus 9. We multiply these together, and we get something like 10 to the power 3. Let me try. This is 10 to the power 3. About 1000 nanometers. Maybe you can multiply this by a factor of any number from 0 to 1. So we have 0 to 1 times 10 to the power 3 nanometers. Now, when you see this, some of us might remember that there is a range over which we can see. So what is the range that, or the optical range? Can I have a couple of comments from the class? What is the range that humans can clearly observe in nanometers? I can expect a couple of comments from you. You can enter them in the chat sessions. Maybe my chat sessions, I'm not looking at it. Okay. Sergio, I'd expect you some. Okay, you were right. I see here 600. Besmir, make clear your comments. I think you are correct. We are talking about nanometer. Okay, so the visible range that we humans do observe is something in this domain. Okay, so we commonly refer the visible range or the colors that we do see something in the order of from 400 to 700 nanometers. Okay, so this 400 it's a blue color, and here the 700 it's around 630, 660 with the red color. But this is the spectrum that we do see, okay, from the blue to the red. And it looks like we are kind of lucky, because if you want to see our smallest components in our human bodies, in our bodies, which is going to be a cell, and we have to measure, because cell, celiza, they have approximately this size, okay? So they're around 10 to the power minus 6 meters. And it looks like, to see these, we can use a wavelength of this range, okay? So if you are using a microscope with this range, it's also safe, because it's not going to get into our eyes without observing it. But if the wavelength is a little beyond this domain, where, let's say, so this is smaller than, let's say, 1064 nanometers, this is a wavelength which is very easily or commonly produced in lasers. This is also very scary, because we don't see this. Okay, so if you don't see this around the room, it might end up into your visual system, into our eyes. It will damage it, because we don't even see it. Okay, but we see it. It looks like we can see this domain. We can use this domain to observe, to use this in microscopes. And that's the common sense of why, when you were in the 8th grade or 9th grade, when you were in the biology class, you could see with a white halogen light, you can pass it through a material or some blood cells probably, and you could see nicely, and you were very happy, including myself, when you saw these small biological structures in the microscope. Okay, not recording it, but you could transfer the information through the light, let's say from the light. So here you have the light source, and let's assume that this light source is 400 to 700. And then the light is going up. This is the light source. You put here a material, specimen, not material, it's some specimen that you want to see, specimen, which biologists are very interested to get this information. And then these were the numbers in the. So now here we have. So this is a specimen. Imagine that here we have some construct that you want to observe, and this wavelength is going to pass through this, and it's going to come to a detector. This detector, it's called, you may remember, it can be anything which is called a CCD or a CMOS. Okay, CCD and CMOS. There are two common detectors which are used for image acquisition, and the newer version is CMOS. And if anyone asks you as engineers, what does the newer one does better than the old one, you should always come with with the answer that it is more energy efficient, and that's true. Wave produces CMOS only for it to be more energy efficient. This is what we are really caring in the last 5 decades, or let's say 3 decades. Everything was produced at least like 56 years ago. In the last, at least in a shorter amount of time, we have been optimizing these old units in order for them to spend a lower amount of energy. And this is not only that you are saving the electricity bill at the end of the month, but it's also essential because these components, we want them to make them as small as possible. The moment we make them as small as possible, they generate a lot of heat per millimeter square. Generating more heat, this brings some problems. Then heat will make a device, it will damage it, or it will change much faster, and you might lose the operationability of these devices. So the idea of having energy efficient units is not only energy saving, but it's also making sure that these devices will not lose their functionality because they get warmer. Okay, so that's why the cooling process is a very essential one in every device. So this was a story, very wonderful pieces of machinery where you have pixels as small as in the order of 1 micrometer, even a little smaller. Now, these small units, which are as small as a micrometer, they are like small agents that can gather a charge as a fluid. Let's imagine we have some light source here, it's passing through some empty region, and then it's going to light up this a lot, okay? But then another photon, a group of photons is leaving from here, is going through the specimen, and this specimen or sample, it has different relative permittivity. So this parameter here, so let me draw it here, but here where we have the specimen in that you also see in the biology class, the relative permittivity here is different, and for this reason, the intensity of light, when it goes to these pixels of the CMOS, will be low. If the intensity of the light will be accumulated in that specific chamber, not chamber, but area. So this means that if we are to transmit these 2 specific pixels into a screen, we transform these as, let's say, this will be a dark, I don't have a black one, but assume that we have 2 pixels. This is bright and this is dark, okay? So these are 2 pixels which the final results that we see these into when we are imaging them, it's a function of all, or it carries all the information or the convolution of the information as it is passing through different regions. Okay, this is empty space, epsilon 0, all the intensity is all transferred over there. But here we have a material which we are observing in a microscopic scale. Intensity is lower, that's why these are the pixels. So this is a bright pixel. Okay, this is a dark pixel. Now, with all this discussion, what is relevant to our detailed information that we can extract regarding the properties of the material? The idea here is that what we're going to see in wave propagation or in electromagnetic, in this specific factor, e to the power I alpha, not alpha, let's say I Tz. Okay, so this represents the propagation of a wave as the Z is changing. Okay, so as you are moving across a region, this is how this is the propagator. Let's call it this way. But now, the moment that we have regions of different relative permittivities, this is not going to be the same. Okay? This K here, this propagation constant, which you have seen and you know this very well from the latest chapters of when you did the class on electromagnetic field theory. This number now is a complex number. Okay? So if this is a complex number, this means that here we're going to have something like alpha plus I beta times z. Okay. Now here we have, as a result, this will be left with E I alpha z times E. We are going to modify these factors to some degree because of the properties of matter, or because of the properties of how light interacts with matter. And it looks like we can see it clearly on the board. So and now you also know that this factor is a factor which decreases the amplitude of a wave as z is changing. And we know that an exponentially decreasing factor or quantity is a drastic change. So even for a small thickness where the relative permittivity is different from 1, we might expect a measurable effect. Let's call it this way. Okay? We might expect an experimentally measurable effect, and we'll be able to detect it. But now overall, at least we understood that what we have learned before, or the essence of how the properties of matter affect the light propagation in those, we can extract it in this way in a beautiful field of microscopy. Now, this was regarding how much the brightness can be changed in between 2 pixels. Okay? We can observe this just looking at this beta. That means that the transparency changes because beta, let me say it this way. The effect of beta on the images that we acquire, it is an indication of the transparency level of a certain material through which a wave is passing. Now, we have also another interesting parameter, which is here this oscillatory factor. So this exponential, e to the power I alpha z, we can easily figure out that that's an oscillatory function. Okay? It does not attenuate the wave. It does not lose the wave. It does not cause the wave to be lost as a function. I see a couple of comments here: transparency or illuminance. Well, I have a comment here. Thank you very much, Ionel, for your comment. You're asking me, is this transparency or illuminance? Let's think about this one. So this beta illuminance, let me think actually, this illuminance, how we define this one, or illumination, or Ionel, can you, I thank you for your comments in the chat section, but I guess we could call it transparency. To all students in the class, I really want to remind you to have a look at the chat session, also to get a feeling of, or at least to get a possible list of equivalent principles or equivalent concepts. They are very important, at least when you compare them or when you analyze those. Probably I can still vote. I can keep my vote on, because it's election time, you know, for very important political systems around the world. So my vote is to keep the transparency factor for this beta. Okay, I call this transparency, or as an indication of how transparent a medium is. Okay. Now this was the first important factor which we can extract. I have another. Okay, thank you. Yes, please. I invite all of you to interfere or even to interrupt me to make clear a couple of essential concepts. And let's not forget, this is just the introduction part, but I'm just trying to offer a feeling of what's the use of these electromagnetic waves principles that we're going to learn in this class. So then again, this was one indication which is reflected to this parameter. At the same time, we have this other parameter, which is an oscillative function, which can be used also in microscopy, because it will produce a signal which is going to be a function of the thickness of the material. But for this one, I need a relatively better drawing. So we can take away the waves of the sea. Okay, it's also late November. Sorry, it's early November. So let's take them these away. And now let's think about a system where, again, we have a light source. Let's say that it's 400 to 700 nanometer. That's good. We have here a material, a specimen that we want to see this in a microscope. Okay, and now here we can have a material which has a thickness of, let's say, a few micrometers. Let's call it 4 micrometers. The wave that is propagating, we're going to have a wave which is going to, let's say, it starts from here, it will go like this, and then, since here we have this specific material, this wave is going to be probably a little shorter. Okay. Now, what we have here, we have a delay. Okay, we have a delay, or we have a phase change. We have a phase change between two waves which are propagating at an edge, or right at the edge of a specific object, and then once they come up, you notice that there is a phase difference. So you don't see the crest or the maxima of an electromagnetic wave matching. Why? Because this was a different medium, a different index of refraction, a different relative permittivity, affecting also different alpha and beta, which are written here on the board. And this phase difference is a very important piece of information which can be extracted and used in microscopy. So this difference in phase, we have the technology now. It has been for quite a while, since the development. I think it was Zernik who got the Nobel Prize for that, how to convert a phase difference into a potential in the voltage difference. And now this is how, where the wavelength of a light is comparable to the object that we want to observe, and at that instant we can critically we can make use into understanding the behavior of very important elements in science, which is biological systems or and medical field. It has a high impact whenever one works with those. Important, and at the same time, I can also add that with a comparable wavelength with the object that we want to observe, we can also have larger objects, but we may be interested into getting a very high resolution. And to increase the resolution, it can be defined as a number of parallel lines of which we can distinguish them. So if we have lines, let's say, and this pair of lines, it can be like 200 lines LP, line pair per millimeter. Okay, so they are relatively small, and nowadays we can produce, we can at least print mechanically lines as thick as a micrometer. If you want to observe those, it's now from the information that we can deduce from the discussion until now, this becomes possible if we get deeper into this lower. Okay, then we can increase the resolution. We start seeing more lines if they are closely spaced together. And for example, you can even push this a little further. When I say this, you can push, of course, theoretically, you can even use 1 nanometer wavelength, okay, or even smaller. But we have also to keep in mind how possible is this, how possible is this to make this one. And recently, new publications came out where they were reporting using optical microscopes, which means that they use wavelength or photons, and observing a resolution of an electron microscope. That was very strange. I mean, it was kind of unexpected. And I was reading this, I can share this one with the class materials. And I noticed that the wavelength that they used, it was something like 10 to 13 nanometers. Okay, 10 to 13 nanometer wavelength. Okay, everybody said that they can produce it, and it has a high intensity because you can always these wavelengths. We can always have those. Okay, even with a very simple. You take the light coming from the sun, you put a prism, you put a diffraction grating. Of course, we have also this one, but having this one at a high intensity is pretty expensive. And it was impressive, and we contacted the company and said, okay, you're making this wonderfully made light source, 10 to 30 nanometers, what is the price? Okay. The price of it was, the company was also very kind and saying it was 1 M. Okay, so that 1 M is $1 million, okay, or euros, depending where you are from, but it was a very respected company, so you can look it up. But yeah, when somebody is afraid to write 6 zeros, you really understand that 1 M is not a good sign. Okay, but it's very expensive. And now this domain of wavelengths, which theoretically we can even say not nanometer, we can put this down to picometers. Okay, theoretically you can say it, but it's hard to produce them. But coming down from this optical range of the photons down to this range, this means that this is so small that we have moved to the wavelength of the electron. Now, this is not directly related to the course that we have of the electrons, but there is one principle that as we decrease the mass, or let's say as you increase the mass of an object, the wave features there are less obvious, but at least electrons have a wavelength which is in the order of 3 angstrom. Okay, so we are 1 order lower than the nanometers, but saying lower than nanometers, we are used to it 10 to the power 2 nanometers. Okay, now this is slightly less than, or this is almost equal to 10 to the power minus 1 nanometer. So this is the electron. So that's why it was impressive result of these photons, which we keep decreasing the wavelength, and it might approach this electron. So electron microscopes are very good because they have electrons that mass, the wavelength is small, and we can do a similar way with the waves, but it is relatively very difficult to both to the region or to the domain of even making very impossible to use those in an experiment. But put a lot of money on it. If what you want to find out is really important, everybody is ready to put a lot of money and to make these experiments possible, meaning using this versus this. And this is also very good, actually, being able to come down into these much smaller wavelengths is also very essential, because nowadays researchers, they can use not electromagnetic waves, they can use electron beam waves to distinguish a specific range which measures anything in around 3 angstroms. Okay. Now you come here with a visible range of optical microscope, you observe 10 to the power minus 6 meters. Now there is a range where it's not easily accessible, but to access this range between 1 angstrom, which is 10 to the power minus 10, to 10 to the power minus 6, it's almost 3 to 4 orders. This range you can scan by currently producing or light at different frequencies, and these are all possible, but sometimes expensive. Now, this is what the class regarding the electromagnetic waves is going to be about, but actually I can provide more details as I go over the syllabus for the topics that we are going to cover. Meanwhile, I can erase some part of this information, and I thank you for some small comments or that you add in the chat session. Now, in this course, what we are going to have, we're going to have 1 midterm, okay? We're going to have 1 final. At least you're going to have 2 homeworks and 2 quizzes, okay? So this will be the grade distribution for this semester. If anything, if you are assigned any, okay, I forgot this one. It will be also 1 project, okay? This class is really a 3rd-year class, and it is very important that you do a little research on specific topics, and in the previous years, students have done a really good job how to search for directions or to do a literature review at least to figure out where these beautiful principles of electromagnetic waves, how they can be useful at least in technology or in research. So this would be your expectations for this semester. If any extra assignment comes up for you, it will be a bonus, which means that your grade will be above 100. Now, I'm going to write this one I'll send this the syllabus in detail with the exact percentage distribution. And you're going to see those in the class materials. Now, another important information is the textbook. For the textbook that we're going to use in this course, I am actually a very big fan of Cheng textbook. So David Cheng, the one that we've used in the electromagnetic field theory class. But now, equally, there is also a wonderful book, which is actually I even have a copy here. You can get this in the library. It's Electromagnetic Waves by Inan. I mean, this is really, at least for a bachelor study level, this is a wonderful book. It has very good exercises. The problem at the end of each chapter, they're not difficult, but they're also very challenging. And it is impressive because it uses applications for a wide range of topics. So I can also add, especially for the waves, for this course, electromagnetic electron and you can have a look again, and I believe they even have recently a new edition of the textbooks by these two wonderful authors is out, so you can even search. You can also find the third edition. I guess they also have a third colleague, a third collaborator that now has three authors. The third edition of this book. I strongly encourage anyone to use this as a reference, and we're going to use this one also in this class. Now, I want to go over the major topics that we are going to discuss. So first of all, the topics which are coherent in terms of the order, both in the textbook by David Cheng and also in the textbook by Inan and Inan. So first, field theory class. So we'll discuss the waves, I mean wave propagation, and also how we can calculate the different factors among the constants of propagation. And if you remember, we analyze the wave propagation mainly in vacuum, okay? Mainly in vacuum. But now we'll start the discussion in waves in medium, okay? The wave propagation in media, and when we talk about media, we talk about two major concepts, which is medium and lossless, okay? So the wave, depending whether a material is conductive or non-conductive. So there is an important parameter, which is the conductivity, and we can use. But now, in an equivalent way of how the index of refraction changes as a function of the frequency or of the wavelength, similarly, a medium is lossy or lossless as a function of frequency. So here, I just want of you. So a medium is not conductive for all the frequencies. Okay, so let me put here lossy lossless F. Okay, the same way that we say Y is a function of X. Okay, so these properties they depend on the frequency. So we're going to discuss the discussion. We'll start the discussion of this course by talking about how the waves propagate in specific media. We'll talk about the energy flow, okay? Energy flow with the waves, okay? Because these waves, they do carry energy, okay? So, and it depends on the strength of the source and other parameters regarding of how much energy you are transmitting through space. But they do carry this energy. We're going to talk about the Poynting vector and other related principles. We're going to talk about the polarization. And polarization is an interesting effect, a very interesting effect, which has a large, plays an important role, especially once one analyzes the reflectivity, transmittivity from one medium to another. When we talk about the different media, we're going to discuss about and the insulators, and then we're going to talk about the different incidents, what happens once a wave is incident on a material at an oblique incidents or non-oblique incidents. And then the class, toward the end of the class, we're going to discuss about the propagation of waves in waveguides, okay? Connection, trying to connect. Okay. Okay. Sorry. Can you hear me? Yes, we lost a couple of minutes because of the I was using the microphone on my laptop, but the laptop is here, so I was not aware. Now, how is the sound? Is all the sound good? Next, you go to comment. Can hear? What about now? Is it? Why is this? Okay. Is it still bad? Okay, so I guess I have to connect back from my laptop. There's one. Okay, so Подожди, микрофон или камеры? Микрофон и камеры будут пока пасы большой. А что это? Так, шум ще сусе, айсан бъдат ексилни, а може тиш да ще джеро. Kako se zove model? We thought these things were a little better actually. I mean I don't hear it all actually. Well, I closed my speaker. Because to reduce interferences, I've turned off the. Actually, I don't hear the tones that they are. Okay. Факт, чего? Këto dua pak ndihmë duhet të thoni që atë vazhdojmë me mikrofonin e kamerës, apo atëherë Direkt już ma się susę, pontu. We're going to solve a couple of examples today. Możemy tu решения. Достаточно di microfoni va bine maximums. Schimb ce te bun. Ok, deci ce камня tu решения. Atterre. Ce se frecvență și determinanță. Să faceți ales. Sigur de ce se ales, ok, depois muda a review. So, okay, so text is here, it's just the response of the wavelength. It should be equal to the speed of light over the frequency. Okay, so regarding this, we can even check the units for sure. So the speed of light has a unit of meter per second. Okay, meter per second, and 1 over frequency will be here 1 over second. Okay, so this 1 over second, this means that this is so the unit will be meters. So the moment that the units are okay, then we can move ahead and check the numbers. So the speed of light is 3 times 10 to the power 8 divided by the frequency, which is 4 times 10 to the power 7. This is 4 times 10 to the power 7. And from here, if we get here 3 over 4 times 10, and this makes equal to 3 divided by 4, it's what? Half of 3 is 1.5, another half is 0.75. So here we have 7.5 meters. Okay, so apparently this is the wavelength. And what else we can express from here is that this is the we can also explain the couple more relationships, but meanwhile, before we go to another exercise, we want to remind each other that here the relevant other parameters that we can extract is the propagation effect constant K, which is 2 pi over gamma. We can also extract the omega, which is 2 pi f. Okay, so here the frequency is 14 megahertz. Here, so we have the angular frequency. So it will be 2 pi times 14 times 10 to the power 6. Of course, this is the unit. just small reminders regarding the electromagnetic waves are the principles of or is a discussion. Okay, so we have the Maxwell's equation, but the Maxwell's equation we can reveal or can extract important informations, especially if we write them in the complex notations or in the phasor notation. So if we use the phasor notation, we can easily extract results. And these Maxwell's equations, we know that they are composed of differential equations which record the curve and the divergence of E and B. So we are sure that these are the important equations of powers. So here we have one of the Maxwell's equations. So let's give an example where E so here we have the electric field, and with this electric field we may go after, and the question is, let's find the H. Okay, so here we have one question, and then from here we can actually use this relationship between the electric field and the magnetic field to find the H. And now this one here we have the current of E. This is going to be equal to so here we can use this equation, which can be derived from the Maxwell's equations, and then here, regarding the curve, so this is a curve or this operator here. And this whole thing is going to be equal to so this is and now at this moment we just need to do this one second. Here for the AX we have 0 minus the z derivative of this vector. So once we take the z derivative, we have minus beta, and 1 minus which is coming from the derivative of cosine. This is 0 plus 0.02 beta sine omega t minus beta z. This is the AX. The AY is equal to 0 because we have a derivative of 0 with respect to x and a derivative of 0 with respect to z. So this is minus AY times 0 plus AZ. And AZ is equal to, we have this factor, we have the x derivative of this with respect to x and the derivative of the 0 with respect to y. So here we get another 0. So finally, apparently, the h, so this whole factor here is equal to this factor here. It is almost straightforward because when it looks also that the h from this result, it looks right away that this h set which we need to find, this was a question for us. It looks like it's going to be AX, okay? We don't know about the magnitude. Well, the magnitude by now is obvious, but it looks like this is along the y, is propagating, you know, the direction is along the y, the h is along the x, and the propagation is along the z. So the propagation is expressed here, okay? So currently, let's try to draw this one. We have, let's assign x direction here. This is y, and this is the z. So we have with a cross right-hand rule. We have along the x, y, and z. So it looks like E is here along the y. This is E. The h is in fact, we have a minus sign here, so h is minus ax. Okay, so h down here. And again, we have E cross h, it gives to us the propagation direction. So it looks like this wave is propagating along the z, and it's completely obvious. Okay, so we have to be a little careful when and we know that the direction of A is equal to the direction of E cross the direction of H. Now, this does not look very correct, but this is the unit vector along the E cross the unit vector along the H. It tells us where the wave is going. Okay, so this is now. So from here, we found what is that H is going to be a relatively simple result. So H is a function of z and time. No, wait a second. Yes, we do have the time still in the expression. So, by the way, this is z. Okay. I hope we have not done anything wrong yet. So, this is H of z is equal to minus AX. Let's preserve the minus sign like this. And then the rest is this is the, let's say, the H. But we don't know, we know that the electric field and the magnetic field, they are coupled. And the moment they are coupled, well, we can extract much more information from these if we use another of the Maxwell's equations. If we apply the curve or the divergence relationship on H, and then we equal that one to what the E was given, and then we can even extract some extra information on this specific parameter data. And to do that, we can use this other Maxwell's equation, which is going to be the curve of H. Okay, so let me see for a moment here. So now we just apply the curve of this parameter, we find, but now we have no common density, so we can keep this, take this out for a moment. And the E, wait a second, okay. So if we're going to take the curve, let me keep this here.
Eso pasa tafsis. Te ecuaționi ajo h në klapë të është ajo gjimë duke që nuk është vanë. Ose nëse që ka pa unë ku e hoqe, ku eliminove. Është të ekuacioni I fundit që ke bërë në kuadrat, ekuacioni I fundit, H që ke ndira të hanë, majtas, jati, e që nëzorën, para këte. Aty poshtë, është një element G, që nuk e di ku e hoqëm.
Oh, Shkabim, no, that's a mistake. You should have this. Është
mbetet kjo, nëse e hoqëm, do thjesht se kuptova ku bë.
No, it's still there. It has to be there. Është qendrore, kjo kujdesh me vetë, po thjesht me harrova. Nuk e pash. Pra jo e qendron, dhe ndërkohë që jo e qendron, nëse të paraqitet edhe si minus AX, tu pastaj është qartë ne, po?
Shumë e qartë, mbet.
Atëherë, këtu të AX-in e heqim, këtu do t'jemi minus 0.02 beta over J omega mu. We have these sine terms. Okay, let's not write these arguments here. And then no component along the y, no component along the x. So this new curve operator, the curve operator, is going to be equal to J omega. So let me write this in there. This is going to be J omega permittivity times E. Okay. So forget this for a moment. Now we have this curve in red is equal to this expression. And then if we do the calculation, we're going to get a more detailed relationship between the E, beta, and the magnetic field vector. Now, I can leave this one as an exercise. You can apply this operator, equal this to this E. Let's not forget that this was initially given for sure. So actually we can have a look. It looks like on this curve, the only non-zero term it will be from the AY. So we can say here, this is AY times the derivative of 0 with respect to x, and the derivative of this term with respect to z minus. So then this curve here, we're going to write this expression. Okay? So the curve here is going to be AY times derivative of 0 with respect to x. Okay, so derivative with respect to x of the 0. Okay, minus the derivative with respect to z of this other term, minus the derivative with respect vector set of the terms which are left here, which is minus 0.02 beta over j omega mu. We have the sine term here. This whole thing is equal to this is a 0, and then we have a minus sign here, we're left with the AY. Minus signs are going away, times 0.02 beta over j mu. And we're going to take the derivative of the sine. The sine term is going to be a cosine now with a plus, but once we have a cosine, this would be now another beta. So another beta comes out when we take the derivative of this. Here we have cosine omega t minus beta 7. So we took care of this section here, that this is equal to j omega permittivity times e. Now we can divide both sides by j omega permittivity, okay? And this is j squared omega squared, okay? So we divided both sides by the same terms, and for sure this will cancel out. We will have the electric field is going to be equal to, so electric field is equal to AY. So this one is equal to AY times 0.02 beta squared. This j squared is a minus sign, so we have one extra minus sign here. Over omega squared permittivity cosine omega t minus beta 7. Now this absolute value here is going to be equal to this absolute value here, and from this expression we can easily get that in principle the magnitude of these factors is going to be equal to 1. And at the same time, I'm just wondering if we have some. I see here that we have, wait a second, divided here with j.
Profesor, po ju janë në katror, ku shkoj aty dhe epsilonja duhet jetë në katror?
Epsilon këtu?
Po?
Jo, epsilonin për të shkoj parë. Jo, të jetë në katror. Se në të jetë në katror, sepse në tani të shumë epsilon. Epsilonin is not good to it. And finally, we get something like p squared over omega squared. We get that this is equal to 1.
Profesor, ma kështu më ka dalë, po kemi bërë atë të parën, do me thënë në kërmin e parë, aty kemi ngatruar një shenjë minus, e kemi lënë pa vendosur, edhe ajo në fund pastaj të del pozitive, mbasi e bën atë gjë në katror. Eliminohet ai minusi, do me thënë.
Si të fillojmë për të dalë njësoj, por?
Ma më ka dalë njësoj, thjesht kur bëm kërmin e parë, ai minusi eliminohet me minusin e asaj, si ta them, do me thënë. Është ajo që curl of electric field është minus j omega mu her h nga formula, jo pak më larg. Është më atë ekuacionet e Maxwellit, po. Edhe në momentin që ne në fillim bëm curling, ai minus eliminoj me minusin, sepse dite me minus para, jo derivati.
Let's check this one. AX equals
Kemi bërë atë post që është në katror AX-i, që shumë zdo 0 plus 0.02 beta sinus omega t, duhet me minus para.
Atëherë ku del plus?
Po aty del plus edhe pastaj ajo tjetra del me minus. Edhe kur e bëjmë përmbi J në katror, atëherë thjeshtohet minusi me minusin edhe del beta katror përmbi omega katror herë një herë I bëhet me I.
Okej, e bëhet plus. Dakor. Atëherë ju e jetë plus.
Po.
We is that part, but let's have a look here. This beta square, okay, that side I think it was important that we missed that one. So now it looks like this beta square is going to be omega squared times these terms, okay? But now this is also, this can be written like omega squared over c squared, okay? Because we know that the speed of light is always in a medium is equal to this factor. So at this moment, we say that this omega squared, we know what omega is, right? Omega, it appears here explicitly. So we get the omega from here. And we know that the frequency, what is the unit of frequency? Can somebody answer me this? It's hertz, right? It's 1/2. But what is the unit of angular frequency? It's radian per second. So this omega, it has units of radian per second. And this radian, if it is radian per second, then this means that this is the unit of this cosine. Okay? So also, so the angle, this is radian per second. Times second, we get radians. And we know that the angles, we calculate the angle of the cosines of radians always. Which means that this omega here, it is 7.5 times 10 to the power 8 whole squared divided by 3 times 10 to the power 8 again whole squared. So this 10 to the power 8 I can somehow 7.5 divided by 3 we get 2.5 whole squared. So beta squared is equal to 2.5 whole squared, which means that beta is equal to 2.5. Okay, fine. Now, we were given this electric field, okay? And what we did is that we applied the Maxwell's equations twice, and we got some information about this beta, okay? And now, this beta is equal to 2.5. What is the unit of beta? Can you help me with this? What should be the unit of beta? Unit? Unit, what is the unit of beta? Let's hear it. No, it's not, well, the unit of beta, we should see it from here. So the whole cosine should have units of radians, right? But here we have beta z. So beta z should be radian something times meters. What is the unit of z?
Meter per second katror?
What?
Meters per second square?
No. Well, let's have a look here for a moment. Beta z is equal to some units we don't know times meters, and this should be equal to radian. Okay? Because we can't sinus in radian. But beta z, beta nuk e di. Z është metër, beta radian. Çfarë do të jetë si aty? Radian per meter. So this should be the unit of beta, radian per meter, because we should expect the units. So for the sake of those, this is what we should get. Okay, so if you remember, by the end of the previous semester, when we did the electromagnetic field theory, we covered examples which are similar to these. Okay? So we're going to start the discussion this semester with a similar approach for sure. And but the new things which you are immediately going to see is the emergence of these two factors, epsilon r and mu r, because now we're going to consider the propagation of waves in medium. Now, do you have any questions for so far? Okay, yes. You're welcome in it, but don't forget this. Thank you for your continuous comments. Okay, any other question? If not, this will be all for today. But your comments, I'd really like to have those, if you have any. Just, I would strongly suggest to go over to try to find the textbooks that we proposed or we suggested to use. Oh, maybe Professor.
Invece, se poprite și îmbrălănți cu mine. Tu peux facă